Hey everyone, it's the host of All Across America, Marco Vig. Thank you for being a listener. The show is free, of course. All I ask of you is that you share it with friends and give us a review on Spotify or Apple. And it would be great to hear from you. We're on Instagram at All Across America or visit our new website, allacrossamerica.com. I try to respond personally to everybody who reaches out, so say hello. All right, on with the show. Podcasting from Portland East to Portland West, from Big Pine Key to Pacific Beach, and from San Juan to Guam, this is All Across America. We're here with Joel Green. Joel is a scientist with the Baltimore-based Space Telescope Science Institute. The institute runs the James Webb Space Telescope, the world's largest and most powerful telescope ever launched into space. Joel's research is particularly focused on the formation of young stars. He has appeared most recently on the National Geographic special Hubble's Amazing Universe and PBS Nova's special Treasures of the Earth, among many others. Joel, it's an honor to have you on the show.
Thanks, Mark. Great to see you.
All right. Well, I guess we could start the difference, and maybe they're the same, between an observatory and a telescope. And I'm thinking of a terrestrial observatory, Mauna Kea in Hawaii, your generic store-bought telescope. What is the difference between, the Hubble, the James Webb that's launched into space? And I've heard it on your website being referred to as both a telescope and an observatory.
The dirty secret is I think those are maybe at this point interchangeable terms.
Okay.
So I wouldn't worry about, you could say the telescope is the piece of equipment and the observatory is the facility around it. And in terms of ground-based telescopes, that almost makes sense, right? You're just talking about, having a backyard kind of dome. That's the observatory, and the telescope is the thing sticking out with the optics, right? But, when you talk about space telescopes, the observatory, or even anything, even ground-based telescopes with a lot of infrastructure around them. I mean, the observatory is an extended thing, and in our case, we almost are. You could call my company the Hubble Observatory and the James Webb Observatory and the Roman Observatory, three telescopes that we sort of operate. And in the sense that we provide, so we don't have the hardware on site. We didn't build them. We operate them. The Webb telescope we literally operate because we have a bank of computers that control the telescope, push the coordinates and everything. I would say I don't do it, by the way.
Right.
We have people who are good at that, flight engineers. But we also, in addition to just sort of pointing it, we run the process by which the choice of target is selected. It's very scientifically rigorous to put in a proposal to get time to use one of these observatories, because time is such a precious resource. We facilitate that whole thing. We run the grants program around that, and we pull down the data, and we receive the data from space, and we archive it in our mainframe and then online as well. And it is all data from all the NASA telescopes is public within a certain amount of time, often immediately, but certainly from Hubble and Webb, the longest that it's private is for the year.
A year, okay. And just maybe you can describe the difference between Hubble launched in 1990, Webb in Christmas Day 2021, and then Roman is scheduled to launch in 26.
Yeah, I think so. Maybe it might be 27. My colleagues might question. Anyway, but 26 or 27 for Roman. It's very soon. That's right. So Hubble is older than many, even millennials.
Right.
It's an observatory that it was launched in 1990. But what's interesting about it, I mean, if I could go on a little tangent for a second,
please.
It was conceived as the Space Telescope. It was just called the Space Telescope, and this was in the original idea was in the 40s. But in the 70s is when kind of people got serious about this in terms of funding and plans. And so there's something called the Large Space Telescope was supported by Congress. It was built. It was contracted out, all the piece, the optics, the telescope itself. And in the early days, I mean, it was long enough ago that the early designs had it, still using film to take images and drop the film canisters into the ocean or something. And people were going to, thankfully, digital technology happened before Hubble got up there. It would have been a lot of weird expeditions with boats to retrieve.
Right.
data.
Right. 24 pictures on a roll
Yeah.
of film.
And I think part of the timing was, we were sort of winding down the moon missions, and you had the space shuttle was this great new facility that this reusable thing, and there were a few of them. These crews were wanting to find things to put into near Earth orbit, and so Hubble was built to take advantage of the idea that it could be launched and refurbished, serviced, which is good because it definitely needed it. James Webb and Roman are not built for servicing, right? They're not built to be launched on the space shuttle, so they're really quite different things. Usually, what sets their sort of parameters is how big of a thing can you stuff in the shuttle cargo bay in the case of Hubble, or how big of a thing can you fit inside of a rocket tube in the case of Webb. In the case of Roman, it's a little bit different, but we can go into that later. It's pretty cool though, because these design. I mean, there are a lot of concerns. When you want to put telescopes into space, there's challenges, there's decisions you have to make. But it's all worth it in many ways because you get out of this Earth, which messes all of the astronomy up. And once you're up there, there are a lot fewer obstacles to really good observing. There are certain ways that can help you, and certain ways where it doesn't matter so much. And so that's why some facilities are on the ground because they can basically do their science just as well that way, and some go into space.
How big is a James Webb telescope?
The Hubble mirror is about 2.4 meters, which is about 8 feet diameter. And it's in a tube that's about the length of a school bus. It's actually a pretty similar dimension to a school bus. So,
Okay.
but when we talk about mirror size, we're talking about the diameter, not the length. And for Webb, it's an 18 hexagon um, composite, essentially, of 18 individual mirrors. But the total radius or diameter of that hexagonal space is 6.5 meters,
Okay.
which is about 20 feet.
20. Yeah.
So it's several times. It's about six or seven times the collecting area of Hubble.
Wow. Okay. And in
So,
you're saying the school bus of the Hubble, how big is the other instrumentation, the tube, so to speak?
well, Webb is interesting. So it is not in a tube. So it doesn't have, and that was partly so it could fit in a rocket. So they had to come up with a way to get Webb to work without being protected by a tube. And so they did it by saying, well, we're not too if we put Webb 1 million miles away instead of a few hundred miles up, it's not going to be hit by debris so much. It'll be hanging out at some distant Lagrange point in space. And then the question was, what are then the sources that would how will light mess it up? And it turns out that the main problems are the bright objects nearby. So the sun, the Earth, and the moon are all really, really bright as far as Webb is concerned. So you want to put Webb in a position where it can block the light from those three objects at the same time and look out everywhere else. So what they did was they made this really clever sun shield, which is the size of the area of a singles tennis court. And it's a bit big, but 6 layer, but really microfiber thing, imagine like aluminum foil stretched ridiculously thin over 70 feet, but about 6 of these layers. And then you always point that between the telescope and the sun, which is so if you're at the second Lagrange point, you are at the stable point where the Earth, the moon, and the sun are all in the same direction.
I see. Okay.
And then the additional advantage that you can put the solar panels collecting the energy collection on the bottom, which is the side that gets exposed to the sun.
Wow.
Right.
Okay.
So you get your energy, it's super hot. And then on the backside, it's super cold. It's protected from light, and you do your observations. The Roman
Wow.
Space
Okay.
Telescope will look a lot like the Hubble.
Okay. And
A lot like the Hubble.
where is the James Webb telescope now? How far is it from Earth?
So that stable point that I talked about, which is like a point where the gravity balances between the Earth, Sun, and Moon, it's not a perfect stable because it can drift away from there. But that is essentially 1 million miles directly away from the sun from our perspective.
Wow.
So if you look up at midnight or whenever the sun is exactly behind you, the other way, it's 1 million miles that way. That's the stable point. Webb actually orbits it in a small halo about 100,000 miles radius.
Wow. Okay.
So it's sort of in that area.
And so that's essentially its racetrack, and it doesn't move from that course.
It stays relative to the Earth in that position all year.
Wow.
So it orbits the sun at exactly the same rate that the Earth does.
Wow. Okay. And how long will it be up there for? I mean, indefinitely or?
Well, because that point isn't entirely stable, to actually stay there, you do need to burn fuel to course correct and stay in that halo orbit. So
I
the
see.
ultimate
Okay.
lifetime limiter is when you run out of fuel, it'll go tumbling off into space,
Okay.
and then
And
and the minute that it faces the sun, you've destroyed the
you're
tunnel.
done. But I mean, Hubble's been around since 1990, so we're talking 34 years. I
Hubble
mean,
doesn't
what
have this problem.
Hubble doesn't have. Okay.
Well,
So
one,
I
it's in a
mean,
tube.
it's in a tube, right?
Second is it's not really a mid-infrared telescope. So Webb is an infrared telescope, particularly mid-infrared. Well, it has several capabilities. It measures light that is redder than red. This is light that's longer wavelength or high or lower frequency than our eyes can even detect,
Okay.
and actually over a considerable range. Hubble measures light that we can see, and also a little bit of infrared, and also on the other end, ultraviolet, which is a little bit higher energy than our eyes can see. It's more violet than violet. Uh,
So what you're saying is Webb does not replace Hubble. It complements Hubble in many respects.
Yes, that's right. No, they don't. They have only a tiny amount of overlap in capability at all. And
Okay.
even that isn't a perfect overlap, as we're discovering. If you want to do an observation, there's a small part of the infrared where both telescopes can observe, but even that, they're not the same because it's not just the wavelength coverage; it's the filter. When you have a telescope, you can put in filters that screen for different kinds of light. Hubble and Webb don't have exactly the same filter set. So even in the overlap region, they are different. And that sounds kind of pedantic, maybe, oh, there's a slight color tint to one over the other. But people who measure things like the expansion of the universe or acceleration of dark energy or whatever, they are relying on extremely precise measurements of the brightness of things. And so if you don't fully understand the relationship between, let's say, the brightness you observe with Hubble and Webb, because the filters are slightly different, you lose precision, which means you misestimate the age of the universe,
Right. Right.
or the Hubble constant, which is a big debate. But yeah,
So the James Webb is a million miles from the sun. How far into the universe is it seeing?
so Webb, because of its infrared capability, can see light that. So well, like, the first thing is the farther away you go from us, the more galaxies are receding into the background. They're going farther and farther away, faster and faster, and that's because the universe is expanding. Then there's this new thing that was sort of discovered, um, that the universe is not only expanding, but in fact, on large scales, it is accelerating in a very mysterious way that is where everything's repelling. So it's
Wow.
actually getting faster. We don't have a current physics explanation for this. It's just an observed fact.
Wow.
Um, and even that, exactly the acceleration, there are a lot of debate. I mean, that is not settled, the exact rate at which things. But the point is, when you accelerate, it's you're moving away from somebody, and that's you get the Doppler effect. This is the same effect if you hear a car drive toward you, and then away from you, you hear "Meow."
Right.
So you hear the pitch be really high when it's coming toward you, and really low when it's moving away from you. So when it's moving away from you, that means that the light, the pitch, which is sound, is shifted to lower frequencies. The same thing happens when you stretch light waves out, so they get shifted to lower frequencies. So that means things that are blue become less blue, they become red. Things that are red become infrared. Things that are infrared become microwave, et cetera. It goes down to the lowest frequencies. But that means that distant galaxies are, even though they are, if you were standing in them, they would look like our galaxies to our eyes from this distance over the stretch of the universe, they appear reddened far into the infrared.
Okay.
So with Hubble, it was clear that we were we had ways of detecting galaxies all the way back to a few 100 million years after the Big Bang, like 400 million years. At that point, it's not that there weren't any galaxies, because all the galaxies we were seeing still looked like developed galaxies, at least to some level, but they were being shifted out of the light bands that Hubble could observe
Okay.
farther into the infrared. So Webb gains in that way. It takes you can go much, much farther back in time because you can see the galaxies that are further reddened. Also, it's
Gotcha.
bigger, so it has more sensitivity, things like that. And it's just got a more modern computer chip. And, but the main advantage is the infrared. So Webb can see a lot farther back, and we don't know how far it will see, but we are currently mapping that out. And it certainly has spotted galaxies 200 million years um, after the Big Bang. The question is, at what point
Jeez.
are so we know we have two data points. We know that there are these galaxies that Webb is seeing, and we know that at the very beginning there was a Big Bang, and there was all the particles kind of coming out. Light escaped at this moment when the universe became thin enough that the photons could all get out. And then at that moment, the universe was dark because there was no light left. It was just particles hanging out in the darkness. We know exactly when that was because it made a huge flash, and which you can see in every direction, which we call the cosmic microwave background. That was 300 or about 400,000 years after the Big Bang. So 400,000 years after the Big Bang, you have a bunch of atoms and particles. 200 million years after the Big Bang, you have galaxies. How do you get from one to the other? That's what Webb is trying to figure out. How did the first stars and galaxies assemble from the dark, not dark, but unlit material that was sitting around?
And now you call the Webb telescope like a time machine that you're able to look into the past. Is that infrared allows you to do that?
Anything that can see distant light can look into the past. In fact, anything that can see at all looks into the past. So if I'm standing next to you at a restaurant, then I still see you as you were a fraction of a second earlier based on the light travel time from you to my eyes. That light travel time only gets worse as you get farther out. So
I
our
see. Okay.
galaxy, is like 50,000 light years across. So within our own galaxy of stars, things could be hundreds of years out of date, thousands, but other galaxies are millions to tens to hundreds of millions of light years away. Then things get really delayed. And of course, the most distant galaxies are actually all the way back to the Big Bang. So you can go, you could basically light that's been traveling for the whole existence of the universe, 13.85 billion years,
Right.
has traveled 13.85 billion light years to get to us. So that thing that was that far away 13.85 billion years ago is also as we see it as it was 13.85 billion years ago.
Wow. Okay.
And then but now of course that thing has now had 13.85 billion years to move and do whatever, and we're never going to get current information, right?
I see. Okay. So that's the rub is you're seeing the time machine, but you don't
Have
know
to see it
actually.
past.
Right. You have to see it past. You can't see it in the future.
You can't see the present,
Or the present, right? Correct. Okay.
much less the future.
Much forget about the future. And so, what are people looking for? And you said that the time is very important, and researchers are essentially submitting proposals to say,
Yeah.
"Hey, we want the Webb telescope to point in this direction to pick up." What how does that work? Is it researchers from all over the world? Is it I don't know, a committee of folks that is reviewing these various proposals? Is that done at your institute? How does that work?
Well, yes to everything you just said. I'll clarify. Yeah,
Okay.
essentially everything you said was correct, but
Okay.
I can give a little more detail. So
Please.
the telescopes, both Hubble and Webb, are what we call general astrophysics observatories.
Okay.
They may have been pitched with some specific scientific discovery in mind, but what's cool about them is that anyone in the world, if they have a good enough science case, can write a 10-page proposal with the technical details and the plan and what we're looking for, requesting to use the telescope to do either Hubble or Webb or both together. That's another possibility, or even other observatories. Uh, you can request time and essentially to perform a project. Then you have to explain why you need that much time to do that project, what results you might expect, although you can't know because you haven't done it, and how is that how can you do because it's so precious, why is it you need this telescope to do it, you can't do it with some cheaper facility that exists elsewhere? So these are
Right.
all factors we think about. These are called proposals, and there's calls every year, and actually even in the middle of the year too, for ideas and proposals, and essentially a massive competition. And so anyone could submit a proposal. Now the panels that we convene but are not allowed, because I work at the institute, are actually not allowed to be on a panel. We are not given any advantage for being the ones who run the telescope.
Wow.
Uh, but we put, we call essentially the community. We look at the whole community. We pick 100+ astronomers on different panels to judge the proposals, rank them against each other, and then essentially we pick the top X% with some other economies and efficiencies of scale, right? You need to be able to fill the schedule. You need to pick things that are not competing with each other. You need to, and the schedule is sort of you're basically picking stuff, a reserve and a roster for the whole year's worth of.
Right. It's almost like you need an administrative assistant to figure out calendaring.
Several. There are computer parts to that schedule optimization, and there are people things too. It's an interesting cooperative venture, basically, between kind of an algorithm and people, but then what people specifically need. Also, things can be interruptible or have interruptions or have priorities over each other. I mean, it's a really complicated formula that they kind of put together, and they revise it constantly. But the idea is that the basis of this ranking is the peer review.
Right. Okay.
So the next call for James Webb observations is due in mid-October, and that's
Okay.
I'll be writing I have some ideas for that. And they only select about 1 in 10 makes it through, because because we get about 10, even with the fact that it's got this, you have to write this onerous proposal and explain all this stuff, and even that we still get 10 times oversubscribed.
Wow.
For the amount of time we have. So it's great that people want to use them. And this is essentially true of, essentially everything I just said is also true of Hubble, with the minor exception that Hubble, although we have a whole year's worth of data, we actually make plans on weekly timeframes. Hubble's a little less automated.
And so October 24, people are submitting the proposals, and I'd imagine a scale of months later, they find out, let's say it's January 25, they find out. When will those people get time, essentially?
So that cycle, those proposals begin in, I think, the fall of 25.
Okay, so it's a year out, essentially. Okay.
Yeah. They need to have it in place. And there are sometimes ones where you say, no, I can't wait that long. I need it now because this phenomenon is happening now. You can make a request like that.
Okay.
It's adjudicated on a rapid timescale.
And so how many different proposals if 1 in 10 make it, how many different proposals are actually being launched probably long term in a given year?
About 2,000 are submitted. The all-time record was the last call for when it was 2,000 proposals. Usually, I mean, between 1 and 2,000.
Okay.
And then so between 100 and 200 are accepted.
Okay. So we're talking.
And not all proposals are the same
time frame.
Yeah. Some of them could be done in an hour. Some of them can be done some of them require months, or a week.
Wow.
And you have to wait that.
And so is it all essentially because it's open source, it's free for the scientists? There's no fee, I would presume, to use it, but they have to make their data open source within a year of the collection.
It happens forcibly, whether or not they do. It's not even up to them.
Wow.
We open the archive. So basically what happens is the data come down whenever they come down. We provide archive access to the principal investigator of that program. And then a year later, those files automatically enter the public domain.
Wow. Okay.
So then now it may be that the scientists can interpret them better than other people, so they still might have a better product, but that's up to them.
So that's their window, though, where they're kind of
encourage people to publish.
Yeah. Right.
And there are lots of debates. This is a hot topic. Are having proprietary periods a bad thing? Do they stifle competition? Do they make it, institutions that don't have a whole lot of, direct access or a lot of, technical know-how might have a harder time jumping in on projects that are really competitive. And there are lots of ways to debate that, because the advantages to a proprietary period are obvious too, right? It's the team can do reasoned science over that year without worrying about somebody else wiping their data and publishing it incorrectly. So, I mean, there are reasons you want that. Also, data that comes right out of the telescope, especially early in a mission, is usually not as good as data that comes out later
Gotcha.
because we run what's called calibration observations, which is we do things that are not specifically for a scientific discovery, but a substantial portion of the time of the telescope is let's look at something we know what it's supposed to be, see how much we missed that by, and put those corrections in and help people fix their data
Gotcha. And so how often are those recalibrations being done in a given year?
all the time. With web, I don't know what percent. I think I guess it's about 10% of the time. Maybe it's 5%.
Wow. Okay. So a
Might be
significant
five.
amount is wow. Okay.
With Hubble, it's actually much more, but it's funny because Hubble is interesting. Hubble, as you know, orbits the Earth really close, unlike Webb. Hubble is zooming around the Earth every hour and a half. So it's only about 300 miles up. Half of that hour and a half, that's called an orbit. You get assigned orbits with Hubble time. And half of that time it spends in Earth's shadow. We're not being able to see anything. So during that half is when you do a lot of calibration with the shutter closed.
Makes
You can do
sense.
things without actually even looking at stars, and so a lot of the calibration of Hubble happens during dead time. Basically, Webb doesn't have any dead time.
Wow. And so you all are essentially operating the nerve center, the air traffic control for Webb.
Yeah,
You said, I mean,
we
is there
used
a
to do it for
person?
Hubble.
Is there a person with a joystick? I mean, or is that all done through computer programming? Is there a control center? What does that look like?
It's really neat. On the third floor of our building, there's something called the Mission Operations Center, or the James Webb Mission Operations Center,
Nice.
which is a bank of about a few hundred computers
Wow.
that have people at not every station, but they're around. And during the early part of the mission, when they were trying to launch it and get it into place, it was, I mean, chock full of people. Now, for routine operations, pointing, you need 35 people, but still 35 people to
Wow.
operate a telescope, and that's just literally just running it, checking,
Wow.
calibrate, and making sure it's still doing what it's supposed to. Is to take, making sure things are operating, execute the next observation command. And so this is done by people using machine code that has been
Okay.
written to operate the telescope through various connections. And so this is hosted in our building, and a lot of the flight engineers are a mix of people from NASA's Goddard Space Flight Center,
Hmm.
and who is sort of our boss essentially, and then
Okay.
some support scientists from our institution.
So are we talking 24/7,
And
365?
24/7, 365.
Wow. Okay.
So
And
there
you
are
mentioned
obviously shifts.
right. And you mentioned NASA. How do y'all work with NASA? And
So I work for what's called a contractor.
okay.
So what that means is I am not a civil servant. However, everyone who, all the scientists, there are a bunch of people who are civil servants at NASA Goddard. So let's say that NASA wants to launch the James Webb Space Telescope. They have to find a group that will build it and work in public-private partnership between Northrop Grumman and NASA Goddard, other things like that. They had to have a group that would operate it, which at least for the moment is us,
Okay.
and do the science in liaison with the community. And I think what's special about the place I work, which I'm really proud of, is it's an amazing intersection of scientists and engineers and communicators, people who can do news, things like that, writing. We do a lot of education and outreach to the public too. So that's kind of been a strength, is that we have this institute was founded to do this for the Hubble telescope. It was literally a contract bid between Johns Hopkins and Princeton for where this facility to run the large space telescope in the 80s would be hosted. And so they built us a building. It's sort of rented from
Okay.
Hopkins. We are not Johns Hopkins. We are NASA contractors.
Okay.
So it's cool, I believe that Space Telescope is probably the biggest concentration of astronomy PhDs in one group in the world.
Wow.
About 150. I mean,
Wow.
there are only about 10,000 PhD astronomers in the world, maybe 20,000. But we're probably 1 or 2% of them are in our building.
Wow.
So
Okay. So
it's
so
it's pretty nuts.
you're one of 150.
Yeah, yeah.
Wow.
Yeah,
I'm
it's not, and that's the astronomers. Now, our whole company is about 800 people, right? That includes
wow.
mostly software engineers and developers, and but and support staff as well.
And so where do y'all get your funding? Because you are a nonprofit, yes?
So we get our funding from NASA. We have sort of agreed that we basically exist to operate space telescopes, and that's kind of what we do. So we're not a
Okay.
company that ventures out into other
Gotcha.
realms, but that
Okay.
is a pretty specific skill set.
Right.
Um, we get all our funding from NASA. That said, individuals at the institute can get funding from other places.
Okay.
Um, you know, but yeah, basically, but what we also represent. So I shouldn't say that entirely. We also are partially supported by the European Space Agency.
Okay.
NASA's counterpart in Europe has a delegation of about 20 people that work on these with us in our building, and there are um, you know, other we're backed by an association of universities essentially. So
Wow.
it's an interesting I love it because it's an interesting job. It's a bunch of people who might otherwise be professors at universities. Instead of teaching classes, my day job is to provide service in support of the Hubble telescope. And then my night job, in some sense, is to do research.
Okay.
So, I love both of those aspects of my job, and they're very different.
So let's hear about them.
Well, the day job is the short-term stuff. I literally am the user support lead for Wide Field Camera 3, which is the camera on board Hubble that takes probably the most famous pictures that you've seen, the Pillars of Creation, all those usually come from us. And so
Okay.
my job individually is to either coordinate or be the actual point person with observers who have been given time to use Hubble, like they've had their proposals are accepted. Now they have to implement them and plan them. And I have to help them, I want to help them use Hubble in the most efficient way possible. And because Hubble is 35 years old, there are some quirks.
I
There are
bet.
things you would not necessarily know about
Right.
using it. And this whole dark time thing makes it very interesting. There are certain ways you don't just purely optimize for time in the way that you would with Webb, where with Webb, the less time you use, the better. With Hubble, it's not quite so obvious because of the orbits. But anyway, that's just one example of the kind of So we help people kind of figure out the best ways to implement their programs. We help them submit their programs, and then we monitor the health of the Wide Field Camera 3's instrument, essentially observations. So some of those calibrations are, let's look at a pretty well-known globular star cluster and measure the distribution of the brightnesses of stars in these fields. Did that change? It shouldn't. Oh, it did? Okay, so something's, happening here, or this pixel has gone bad in the camera or whatever. So I do a lot of that, and those can be very rewarding short-term projects, and it's fun because I get to interact with every astronomer that wants to use the Hubble telescope.
Right. So from all over the
You know,
world.
yeah, I love it. So I get to kind of be user support, and I love the digging down into the calibration to figure out like, oh, is the tungsten lamp that we use to shine on the interior detector, is that getting redder? I mean, these are fun experiments you could do.
Right.
Some of them with the shutter closed. So that's my day job. But what makes this job? I mean, that would be fun. But the reason I wanted this job is I wanted someone to pay me to give me time, in this case, about half my time, to do research on the formation of star and planetary systems. This is what I'm most passionate about in terms of like discovery space and astronomy.
Right.
And actually, Hubble's not necessarily the tool I would use for that. I use Webb as a researcher much more than I use the Hubble telescope,
Right.
um, because Webb is much better at observing dusty star-forming regions and things like that. But it's and historically, I've used many other observatories from other facilities run by other companies like ours, actually. So it's a lot of fun, and I love that they're almost separate communities. I mean, they're not, because you talk with people on both sides, and I think the nice thing about working at a place like Space Telescope is that everyone there loves astronomy,
Yeah.
even if you're not an astronomer. Um, but when I do research and I produce papers, those are the currency by which my my job is known to them, right, to the astronomy community. So in the same way that if the artists essentially are known for the work they produce, right? spend a bunch of time thinking about how to do that, but don't produce anything, they're not an active artist. So there's a certain joy in producing research results that I can present to my colleagues, and they can check, they can find things wrong with it, and we can kind of hopefully make some discoveries together. And yeah, that's the broad difference between the two jobs. Is I try to apply the discipline that I learned in the day job on the short-term projects to turn the research, which could otherwise be an overwhelming uh, you know just sort of morass of a project, into bite-sized chunks that have discernible results that you can put out.
Nice. And so tell us about protostars.
Okay, so this is what I am most. I think that, I mean, I may have a skewed perspective here, but I think that everyone wants to know what's the deal? Like, where are we? Right in the universe. Like, you wake up, you realize you're in a village on a country, in a continent, on a planet. You hear about the solar system planets. You hear that those planets are around a star, that's one of many stars inside of a galaxy, and these are all things we've learned over the past few hundred years. And then that galaxy turns out to be one of billions of galaxies in the universe. And you start to think, okay, so how did you, well, one of the questions you might ask, there are many, is how did the solar system come about? What is the solar system typical? What are the, if it is or isn't, what are the markers that we could tell whether solar system clones are forming around the galaxy all the time? Are our solar systems being born? They are. Spoiler alert. There are. There's about one new star a year in the galaxy, and just on average, but they're actually formed quite. They're not like random. They form in these in the collapse of clouds in large groups. So protostars are what we call the youngest stages of that collapse. So just the basic thing to think about is that our galaxy is a bunch of stars, but those stars are threaded by a soup of gas and dust, interstellar gas, interstellar dust that's kind of everywhere. And normally it's just a very low density thing. But there are places where it comes together and gets denser, and it creates these beautiful nebulae like you see in films and stuff like that. And the denser and denser something gets, the more it shields, the more it's able to absorb, external radiation, which can actually cause the middle to be very cold because it's sort of refrigerating itself.
Wow.
That's the key to forming a star, is cold. Because heat is literally the motion of individual particles, kinetic energy. Heat is how fast and how much energetic are the particles bouncing around. So the colder something is, the less energetic they are. Everything is attracted to each other. So the only thing that resists the collapse of gravity is the shaking. So the colder you get, the more prone you are to collapse. So these cold storage regions end up being starbirth nurseries, essentially.
Wow. So
the sun formed in one of these. And so I want to, but there are many of them active now, and I want to know how exactly do stars coalesce out of the knots of gas? Do they form in a particular way? Are there any trends in the way that they show up? At what point does the gas that misses the star but ends up stuck around it is what eventually coalesces into a disk, which then turns into planets in a plane, and then later those planets can be knocked around and lots of things can happen.
Wow.
I want to know, in each stage of this process, what are the key factors that determine the final system configuration? How common is the solar system, or should we expect the solar system to be? And those are broad questions, but you can kind of drill down into any individual thing. And so we spend a lot of time trying to, wondering, how much of what we see right around us is typical or not.
And so is there a scientific name for our sun?
Sol, I think.
Sol.
SOL, I think.
Wow. Okay. I mean, just because there's an unfathomable number of suns. I mean, there's what thought to be 1 trillion in the Milky Way galaxy, and there's thought to be possibly 1 trillion galaxies. You add, you multiply those two numbers, it's beyond human
10 to the
comprehension.
23 or 24.
Yeah, right.
Yeah, no, that's about right. And that's in the observable universe, right? People would say, oh, well, who knows what's beyond what the light that we could see, right? There could be no end, but that's the observable, like 13.85 billion light year bubble.
And so are you saying that stars are formed in a similar way in our galaxy or in every galaxy, or do we not know?
Well, okay, the first thing I would say is there is a principle that the if that an assumption, right? A postulate that if the laws of physics should work the same everywhere in the universe. And there are ways you can test whether that's true or not. Every time we've done a test, it's basically it does seem to be the same everywhere.
Wow.
So we haven't seen any evidence that there's different laws of physics in different areas. That would make it harder.
Right.
But could be, right? Who
Right.
knows? But we don't think so. So we presume that every galaxy is operating under the same physics, in which case and that there's no special point in the even though you talk about a Big Bang, that doesn't imply a center. It's like asking what is the center of the surface of a sphere, the surface, right? So it's inflating, right? You're blowing up a balloon. You put a bunch of dots on a balloon. All the balloon is inflating. Every dot is getting farther away from every other dot, but there's not like a center. Well, there's a center, but it's not on the surface of the balloon. It's
Not on the surface, right?
some other dimension, right? So I mean, you can imagine there could be an analogous fourth dimensional center to the universe, but whether there is or not, the effect is the same. Everything's moving away from everything else. There's nothing special at any point. So there's no reason to think that it should be any different anywhere else. So that's good. So then the question is, that's in terms of space, but what has changed over time, the universe has become more metallic. It has become more enriched in heavier elements, and so there's definitely an observed effect of heavy elements in the efficiency of planet formation, for example, in
Okay.
conversion of gas to stars or planets. The more heavy elements in general, it's better at converting. So it is suspected that in the earlier parts of the universe that it was harder to make star and planetary systems than it is in the later part. So even though the Earth and the sun are 4.6 billion years old and the universe is 13.8 billion, and so that means we came about in the last third of the universe. There is some bias. I don't think that there are nearly as many candidate Earths from the previous 10 billion years as there are in the last 4.6. So there are
Wow.
things like
Okay.
that. And it's not just metallicity. There's also the types of stars that existed that now the smaller stars live longer, much longer. And so there are certain things that were much more common in the early universe, like exploding big stars and supernovae and violent interactions that could definitely affect all this stuff. So the long story short is we can study all these effects either in the Milky Way galaxy, our own galaxy, or in other galaxies in aggregate. And so there are whole classes of astronomers that study what's called star formation. And what they mean by that is the average effect over a whole galaxy as to, what are the bulk effects. And they get very interesting results about star formation rate and time and stuff like that. What I am interested in is the individual systems in our own Milky Way galaxy where we can resolve details. I want to know what made that star.
Wow.
And that sounds almost picky, but it matters in the aggregate because we could say, well, you know, you only need a few interesting stars to have a case study, right? You're not looking at every one of them. You want to know, okay, what are the odds that something forms that's like Earth or the
Mhm.
sun? And so you don't have to. It's better. The more detailed information you can get about the environment of each star, the better. And so the closer you are, the better your resolution, the more your sensitivity, the more detail you can see.
Wow. And so you had mentioned you work for the Space Telescope Institute. Are you submitting proposals? You said there was some conflict of interest there. How does that work for you in gathering time to use the Webb telescope?
Yeah, no. So let's say that one interesting practice has been that one of the rewards of being the host observatory for a ground-based telescope, or let's say a university that put money into the development, is that they get kind of rewarded with some priority access.
Fair enough.
We didn't build this telescope. We didn't put the money in. We're nonprofit. So we don't really have any justification for having priority access to these telescopes, right? In the most simple sense. So I have no problem with that, and we don't. There is a double blind review process, so
Wow.
nobody knows
Okay.
even who submitted what. what it's the conflict of interest is funny. It's the decision has been, which is maybe not quite as clear, that people who work at the institute shouldn't even serve on the review boards. I don't know if I agree with that, but that's okay. I don't feel like I have to. The community can weigh in. They're perfectly capable of telling everyone what a good program is without the input of every scientist at the institute.
Right.
And so the the key is that we want everyone to realize that it's an egalitarian and fair process, right? That there's no advantage directly from being here. Now, I mean, I know a lot more about the telescope, so I can probably be a little clever, but
Right.
that's just having read a lot about the
Yeah.
telescope. So I think there's a little small advantage in that sense, but it's not one that I think is unfair. I think it just happens to be,
No,
I
fair
know a lot
enough.
of scientists who work on the telescope and can tell me what its capabilities are.
Right, right. And so, often in science, particularly in the world of PhDs, there's the expression that you learn, more and more about less and less. So people are studying, the mating habits, I don't know, of some obscure insect. Do you feel it's the exact opposite in astronomy, that you're understanding that there's more and more and less and less? I mean, because it's just so infinite, the universe. We don't know it's the end point, though. How is how do astronomers approach science that may be different from other disciplines?
I think it's a really good question. I hadn't really thought about it the way you described it, but I like it. I mean, I think there's a generic statement about a PhD is that it is, you're right. You have a foundation. It's like a pyramid of knowledge, and you kind of build toward knowing more and more about a narrower and narrower piece.
Right.
And then you produce your thesis. And then in some sense, at that point, you actually have to rebroaden out again, because you're going to have to, you've really settled this one thing, but now you need to maybe, have a little more general appeal or broaden your interest to see how other things work. And there is some level of translation from one field to the other, one little subfield to the other. But in some sense, you're building a new column out from in our pyramid analogy, it's like there's a second pyramid over here that maybe the bases are connected, but you still have to dig back out again. So
Gotcha.
going from one thing to another is actually quite a bit of effort, the farther away you move from your main discipline. And it's very interesting because there are people who are experts in that thing.
Right.
And so in some sense, it's like a series of pyramids dipping out,
Okay.
or a
Right.
series of peaks in knowledge in very specific things. So I think that's how science works in general, I would say. And it's hard. I mean, it's really, scholarship is you have to do a lot of, when you say do the research, it's no joke. I mean, you do. You need to know at least what people have done and what they have ruled out and what they haven't done to have a good idea as to what to do. So the reason that I can write a proposal for the James Webb Space Telescope and actually have a chance of it being accepted is because I know, because I've read a lot of papers, that this particular question is not answered by anyone else. And also James Webb could probably answer it.
Right. Okay.
Right. That's okay. So all that. But then when you make a discovery, you're right. You pop out, oops, now I've opened a whole new can of worms. Because we know this new fact now, but that implies a lot of other things or leads to a bunch of other questions. Absolutely, it broadens. And I think your point is that astronomy is in its infancy as a science in a certain sense. There are some really basic things we don't know. And we have instruments now that are making large leaps forward. These are not incremental jump. James Webb is not an incremental improvement over the last telescope. It's at least a factor of 10 better. And so and there are other places where we can do that actually, which I'm hoping are coming up in the future. But so you would expect a lot of James Webb's biggest discoveries to be total unknowns. It makes it even hard sometimes because you don't even have a guess.
Right.
And that doesn't convince, people are risk averse. It doesn't convince a panel to give you time if you're like, I don't know what we're going to see, but we want to look at this. Occasionally that will work.
Yeah.
But you have to, someone has to take a gamble somewhere. So right. I mean, this is one of the reasons I went into astronomy is it is not a field that has been picked over, I mean, this is not material science, which I love. It's very practical, but and I know there are many discoveries to make in material science, but this is like, we don't even know what the discoveries we want to make are yet in certain areas.
I mean, is there a sense of, I guess, lack of hubris, a sense of modesty within astronomy because it's such a young science? Because here we are, we're on this little rock, the third stone from the sun in our galaxy in this giant universe. I mean, it's almost the concept of the mountaineer on the summit of a mountain looking out and seeing how small we are compared to everything else.
It definitely has that effect on me. Um,
Yeah.
I actually find it really comforting. Could be okay. So my arrogant, late teens, early 20s something self got really anxious and depressed about the thought that like we could solve the universe and that there would be nothing interesting left to find. Right. Imagine if you had, this is before had done any astronomy training, right? Imagine if you're like, oh, well, I hit the ceiling,
Right.
right? That was my biggest fear. And that
Figured
is,
it out.
what a stupid, arrogant, like teenager thing to think, right? But it is common. So actually, the fact that the universe is so mysterious and so vast with such a variety of questions that we can barely tackle with what we have um, is comforting to me, in addition to
Right.
humbling. It doesn't bother me. It actually makes me excited because it means that there's a lot of things that are possible, like a
Right.
lot more in the
Yeah.
act.
Right.
Um,
So I mean, you'll never run out of questions
yeah.
to ask.
And I
I
pity
mean,
the point in civilization if we ever reach it where we do run out of questions because it's
right.
really
Right.
boring.
Right. It's almost the scientific utopia, I guess, and you strive to get there. And if that were
Once
ever
you
to
get there,
happen, it'd be pretty boring.
you're the dog that caught the car.
Pretty much.
Uh,
But I do look at science as, here we are in the 21st century, but there will be a 22nd century science, a 23rd century science, and it's
hope so.
that sense of, how can we respect science now, but also understand that much of what we know may in fact be proven wrong, or may
Yeah.
just be the most, the very basic elements of what could turn out to be, something much, much, much larger.
Well, I have no problem with someone telling me that I'm wrong. To be clear, I mean, well, I should say that. Sorry, I strive to have no problem with someone telling me that I'm wrong. No, like I wasn't quite sure. Are you asking if astronomers are humble? Because no, I mean, right? Nobody wants to be told they're wrong.
Right.
Like that's awful.
Yeah.
Um, so you want to be right, but the point is to not do if you're going to be proven wrong, you at least want to have put in the effort. Like, okay, at least I ruled out the obvious. Like, you want to be wrong for a reason that you have some control over, or that like, oh, I didn't know that fact,
Right.
I made a mistake. That happens. I have made mistakes, quite a few actually, and sometimes it's been salvageable. There was one time, I'll confess, that I typed the wrong coordinate into a telescope, and I took a beautiful image of the totally wrong object region, wasting valuable telescope time. And funnily enough, that what we looked at turned to have this very surprising evidence for turbulence and shock waves in the cloud, because I missed the star. We were pointing at naked cloud, and that actually was awesome because probably we wouldn't have been approved to just look at nothing, but turned out it wasn't nothing. So anyway, you don't want to do science that way, but
Right.
serendipity is good too. Well, this is
Yeah.
why it's good to have instruments like Hubble and Webb with actually very broad capabilities that can discover things that are not the original intent.
And so the Roman telescope, what is, you said, the Webb is a factor of 10x above the Hubble. Where does Roman fit in? What's beyond that? What's even
Yeah.
next?
So Webb gives you the infrared capability and the factor of 10, sensitivity, resolution things. A mix. It's a very simplified version of its benefits. Roman is actually a much simpler telescope. Webb is comparable in cost to Hubble when you account for inflation.
Okay.
Very similar in terms of in 2024 dollars or whatever. Roman is only one third of those.
No.
It's cost capped at I think 3.2 billion. whereas Hubble and Webb are roughly $10 billion missions over, and those are numbers over 20 years of development. So it's about 500
billion with a B.
B.
Wow.
Yeah.
Wow.
That's about 500 million per operating year for Webb, or about 300 million per operating year for Hubble.
Wow.
So per year, it's I don't know, a fighter plane or something. Anyway, one fighter plane or something like that. Elon Musk could buy a bunch of them and he could build 20 James Webb. But anyway, for us, it's a big deal. But Roman is only 3.2, so that's a third of. So it's not as ambitious of a mission in that sense as Webb. But what it is it's really interesting. The story behind it is really interesting. The National Reconnaissance Office, right, the spy satellite people, basically came to NASA in 2009 and said, "Hey, we have these two exactly Hubble size mirrors, just lying around in junk spare parts. Would you like them?" And NASA said, "Yes." Wait, you're giving us the mirrors for two Hubble telescopes that you just have lying in a closet? Well, the National Reconnaissance Office, I'm sure, has moved on to bigger and better things than, because this is sort of hinting at the fact that Hubble was built in collaboration with a defense company, a defense contractor, right? So I'm sure when they designed Hubble, they were working with government agencies to acquire some of the parts, and I'm sure that some of the design choices were probably influenced by spy satellite technology of the 70s. Anyway, they had two extra ones, and NASA got them, and one of them actually has a flaw. I don't know if it's going to be used in anything, but the other one is fine. And so sort of a every 10-year survey amongst the astronomy community. What are the top projects that we want to do in the next decade? And in that particular one, NASA asked the question, "What should we do with our extra Hubble mirror?" And the answer was the Roman telescope, the Nancy Grace Roman Space Telescope. It was called, at that point, it was called W-FIRST. It's exactly the same size as Hubble, 2.4 meters. It's in a tube like Hubble, but it is 2025 now, or 2027 when it launches, and it has much higher. We have much better detectors than we did when Hubble launched, even that are on its retrofitted instruments. And so the main thing Roman gets you is roughly the same sensitivity as Hubble, but 100 times the field of view.
Wow.
So one Hubble picture is actually quite tiny in terms of angular size, like a little postage stamp. If you take one picture with Hubble, no matter how deep it is, it's only an area that's like it's a few arc minutes on a side, and that is a very small thing. Now imagine multiplying that by a factor 10 in both directions. You take that's about a quarter of the full moon.
Okay.
That's what Roman pictures are the size of four of the tile of the moon, basically, in terms of angle.
Okay.
So what Roman's going to do is going to allow you to take Hubble quality pictures of vastly larger fractions of the sky. That's going to do a couple things. That's going to make you find. You're going to have a lot of chances for serendipitous discoveries and things in the background, because you're going to have huge, beautiful. First of all, you're going to have stunning pictures to the public all the time coming out of Roman. Second, you're going to find things that are unusual, like free-floating planets. There are expected to be a lot of them. You're going to also increase the sample of galaxies at high redshift that we make, because all these things I've said about dark energy, they're based on a few very meticulously tiled fields from Hubble and Webb. Mm-hmm. Small areas, though. We don't know what every single galaxy looks like in all the directions, because to do that would have taken the Hubble telescope hundreds of years. This thing can do a lot more. So we're going to have a much more accurate measure of what's called large-scale structure. And then it also has a test coronagraph on it, which will allow it to start working on detecting what's called high contrast, where you block out the light from the bright star and you look for the dim planet next to it. This is a demonstration instrument. The idea is that if it works, then you can build a better version of it for bigger telescopes in the future.
Gotcha. Okay.
So it's pretty cool.
Maybe we could turn to, and we had discussed this offline, K218b, and just to maybe as a way of talking a little bit more about the spectroscopic signature and how that works.
So I don't know a ton about K218b specifically. That was the one where they detected
Some potential biosignatures of
or at least a gas line. Yeah.
yes.
So the Webb telescope in particular has the capability of using its spectrographs to measure the abundance of different types of gases in the atmospheres around planets. The holy grail of this, the idea of this whole field is what if we found a planet that was Earth-like, rocky, in the habitable zone around a G star? I don't know. Whatever constraint you want to apply. And then we measured its atmosphere and we saw some elements in that atmosphere that were definitely could not be produced by abiotic processes, that had to have an origin of a biological process. That would be the smoking gun for life in the atmosphere of that world, or at least that affected that. For example, if you took the Webb telescope and you pointed it at the Earth, and you'd need a little better. You would need a super Webb. But let's say you were an alien, 20 light years away. You had a Webb telescope is a little better. You pointed at Earth. You waited long enough because you have to wait for Earth to orbit the sun a bunch of times to get this data, and you have to know it's there. So you have to do pathfinders to figure out what these things are, and then okay. But you would notice, for example, the CO2 levels in our atmosphere were rising really fast. That would be a hint that there was something going on, like either some crazy natural process or anthropogenic CO2. So that's exactly the kind of thing that you could detect with a telescope like that. It's kind of cool. But I'm not saying that we're looking for alien pollution. I think that you basically you want to get enough data on enough different molecules at the same time to argue that either this is a very exotic situation or that we think life could be on influencing the atmosphere of this planet, which is pretty cool thought. And I think that is the most likely route for us to find, extraterrestrial life, assuming that there isn't any in our own solar system. That's a whole other, that could happen. Right. We certainly have not ruled that out. That's a different topic. But in terms of going to other places and learning, I mean, it would be helpful if we could find any life anywhere else. Just having 2 data points would tell us a lot about our own origins that we can't figure out just from us.
Wow. And now there's something called the Habitable Worlds Observatory, where 25 potentially habitable worlds are going to be observed. Can you talk a little bit about that?
Yeah. So, I mean, I'm really excited about habitable worlds. That is an idea for basically a super Hubble in certain ways. An observatory like Hubble in the sense that it has visible light, UV, infrared, has similar capabilities, but it's much bigger, and it has a coronagraph or other advanced method of filtering out light, so that it's much more sensitive to close-in planets that can take direct images of them. So this is a pretty cool idea. Let's get a telescope up there. Hubble's aging anyway. Let's get a telescope that's newer and better up there that can do that in a feasible amount of time, has an actual probability of detecting an Earth-sized planet at the at 180 around a G star or whatever, something like Earth. The things that we have now can't do all of those things at once. Webb, for example, is great at measuring molecules in the atmosphere of planets that are really close to their star, i.e., super hot, or really bright, like super Jupiters, or really far from their star, like incredibly cold things. But none of these are Earth analogs. Exactly. I mean, there's always like levels to which things become analogs. So to do that, it really does have to do with aperture size, collecting area, and sensitivity, because you're looking for that one photon from the planet out of a billion from the sun, from the star, that in order to make that direct image of the planet. And that's, I think that's the goal. One of the goals, and the reason it's called the Habitable Worlds Observatory, is that the concept is big enough that it can feasibly do 25. It can check 25 planets in its mission lifetime. Now, the bigger the thing is, the more planets it could do. If you descope it, can't do as many. Also, nothing precludes this observatory from being used for any other astrophysics, right? So it is also an enormous dark energy detecting machine, and it's great for measuring everything that we're accustomed to. So although it's called the Habitable Worlds Observatory, that is maybe the most obvious scientific case for it, but it's really very powerful general purpose observatory. And so I'm really excited that some of my colleagues are, trying to lay the groundwork to do this. You want to build a telescope that's this big, this ambitious. This is going to be more costly than Webb. We need to demonstrate that can be done. And so you need to put some time into looking at what's called technology readiness studies. That's what NASA funds, are these sort of, let's do some pioneer studies. Let's say, what is the pathway to making this telescope? Is it possible? What new technologies have to be invented for that to be a success? There were like 16 or 20 new technologies for Webb to show up. So that's why these things take 20 years to build.
I see. Okay.
And so some of the money in the beginning, included in that 10 billion cost, right, was the development of the technology to build it in the first place.
Right. So I mean, you're almost envisioning concepts, and then you've got to build the concepts, and
it's the whole process. And so you have people who are interested in all these aspects. They're interested in what could we do, how do we get there. I want to use it when it's being built. I want to run it. I want to drive it, whatever. And these are long-term projects. This thing, the habitable world, that's a 20-year path, at least a 15-year.
Wow. Yeah.
And so anyone who's going to use it, I mean, I'm going to be nearing retirement age, right? At least about 60, 70, between 60 and 70 when it goes up. So I may be using it, but I'm certainly not going to be the student that took advantage of it. And so that's the fact that I'm using James Webb. I'm standing on the shoulders of people in the 90s.
Standing on the shoulders of giants. Yeah. Yeah. And so
my parents' generation.
Right. And what do you think in terms of in our lifetimes, will we have a sense if there is extraterrestrial life out there?
So, I mean, there are lots of things. There are lots of ways to answer that question. Okay. I mean, there's sort of the statistical astronomy answer. There's the gut feeling answer. There's the different methods of detection. How effective are they going to be? I can't tell you whether there are aliens that are going to make a biosignature that's obvious on these 25 worlds or whatever that have, or that it might take more work. But I mean, first of all, intuitively, I think, yes, I think we're eventually going to run at least organisms that are not ours, that are not us, that come from a different genetic heritage. I think it would be very hard to imagine that doesn't exist somewhere. Now, but then you start saying, well, intelligent life, that's a lot rarer. Maybe it is. Okay, maybe there isn't a lot of intelligent life, but there could be 10,000 intelligent species in the galaxy, and they would still be separated by unfathomably large distances. So, in some sense, the question is, are the nearest 1,000 stars, do any of them contain life? Because those are the ones that we can reasonably do a round-trip message with because of the speed of light limitation. So the nearest 1,000 stars are maybe within 10 or 20 light years or whatever, or 30 light years away or something like that. So that's a much more limited problem, at least. I think that there's a decent possibility that life maybe even exists in other places in our own solar system. Maybe because it can populate over, right? Maybe we even seeded it by accident. Maybe it's not even an entirely independent life. So I don't think it's impossible. But I also think that it's entirely possible that all you need are, the right conditions. But you have to have we know that there are complex molecule chains, right? We observe them in space. Webb can see them. We know that there are organic molecules. The question is, how do those just exist? But how do you mash them together to make RNA? To make something that can replicate? How hard is it to arrange those conditions? We would love to know how it happened here. And it's not that we don't have an idea. It's actually that we have way too many ideas and no way to prove which one's right. Because the thing about the Earth is it's full of things that have been grinding it up. And all of the evidence has been long erased, right? So everything from the early phase is eroded away. So it would be helpful to find a different place where either the evidence hasn't eroded away or is actively doing it now. That would give us a lot more hints as to what happened here. So I guess my answer to you is I think, obviously, that there are insane numbers of planets in the universe. Every star probably has a planet, and maybe every so often, the real debate, the knowledge is how many of those planets that we find are habitable by whatever definition of life we want. And those are two huge variables. but okay, let's be optimistic and say that it's all over the place. Is intelligent life hard to make? And is it ever going to be close enough that we'd be able to contact it? Those are tough questions. So my gut says I hope so. The reason I'm an astronomer is I got excited about science fiction. So having a universe where we're the only intelligent being seems really weird.
Yeah.
And also having a universe where we're stuck in our one solar system seems weird. But at the moment, that is the reality because we need new physics to get out of here.
Right.
It's not the current limitations are significant, and it's not that anything's impossible, but the analogy I like to make is if I said to you, you think about science fiction movies. If I said to you, is it what? Well, let me ask you this: is it more likely that we will be able to travel faster than the speed of light, or bring back the dead?
Bring back the dead.
So I agree because bringing back the dead is at least a known possible thing, right?
Right.
Like things that are dead become alive.
Right.
Just from birth, right? Clearly that can happen. Nothing, as far as we can tell, could go faster than the speed of light.
Right.
So we don't even have that fig leaf of hope. So, I go back and forth between like, sure, we're going to find it, or, oh, we're just going to be stuck here. I hope that the research that I'm doing will in some small way, contribute to like better models of the universe that we can use to understand what the probability is of running into life.
Is there a potential maybe for some form of life that created, I guess, a von Neumann machine where it's self-replicating that, even though it could be 100 light years away, it's in a von Neumann machine is a machine that creates a machine that creates another into infinity, essentially. So is that a possibility as well, that we could be visited by, some civilization from, that may have existed many millions, billions of years ago from, very, very, very far away?
So absolutely, it's possible. There's nothing that rules that out. I think looking at our own machines, I don't want to send like a Windows desktop.
Right.
I mean, space does suck. Actually, like all of our telescopes break after a while just because of radiation. I mean, so I don't think that you could just float forever without any damage. But if you were clever enough, you can make machines that self-repair and nothing goes
Right.
wrong. Sure, why not? So okay, that could happen. I did make I don't know if it's always emphasized. Like there is this argument that there probably weren't there. We're not as late to the party as you think. I think there weren't as many opportunities to have intelligent civilizations prior to us, but there were billions of years. There certainly could be. So why not, right? I mean, and we should definitely look for that kind of thing. Let's hope so, right? Unless they're dangerous, let's hope so.
Right. But it would be pretty boring to think that we're it.
I like Star Wars, right? I mean, where everybody's just kind of like aliens are everywhere. And, I mean, just to pop in, go to this, I'll go to the bar and drink with a different alien. That sounds awesome. It requires the travel time between star systems to be roughly equivalent to a road trip in a Winnebago. But so we need that.
Right. We'll have to figure that one out first. What would your advice be? And we just have a few minutes left. What would your advice be on, for folks, young people who want to become an astronomer and, pursuing a PhD?
So I think one of the best things, there's a bunch of things about astronomy that I think are amazing. One is it has this broad appeal, right? Everybody can look up at the same night sky unless it's light polluted out by satellite constellations and other issues. But everyone has the night sky. It is a park in a sense, and so everybody hopefully wonders the same thing. So astronomy is the most uniquely international science there is. Also because the facilities needed to make the modern advances really are international, and NASA has a very special role in this. I don't think you could name another government agency in any country that has a positive reputation. I mean, maybe you never heard of them, but nobody sit there and like loves, I mean, even the European Space Agency, you probably never heard of it.
Right.
They've launched some very famous missions, but it's kind of a unique role. I was thinking about the movie Interstellar, I think, where Michael Caine comes out of the out of the little encampment or whatever, like comes out of the tunnel and they say, "Who are you?" And he says, "We're NASA." And I think if he had said, "We're the NSF," it would not have had the same impact.
Right.
But there's nothing, I mean, in some sense, it's a research funding agency. So
Yeah.
I think that just being interested and curious is the best thing astronomy could do for the world is to make people wonder things, right? That's exactly what, you know, everyone, for the person who thinks that there are UFOs landing everywhere, that's fine. At least they thought about it, right? At least they're examining data. They're starting to say, okay, they're saying there is a universe out there. There is potential that could, things that could happen. And okay, I mean, you have to read a lot of background to really have to become an astronomer. You really need, physics and math training and things like that to make, in the sense of making scientific leaps. But it is a science that is so participatory for the general public that anyone can follow along, get excited about, or anticipate discoveries that people want to hear about it. And if it inspires somebody to go into material science, that's great. That is probably more valuable to humanity than what I'm doing. But that's great because at least it's because they started critically thinking. Because all the sciences and arts fields share a common base of methodology and a common understanding of how knowledge is obtained.
Yeah.
So I like it, but individuals are individuals. You're going to run into people that are terrible everywhere, or that are, there for political reasons. You're going to run into people that are maybe not even doing it right or unscrupulous. And then you're going to run into a lot of people, unusually large number of people in astronomy, who are motivated purely by their passion for the field. But people have to make a living, right? So you don't want to make the field so exclusive that people that don't have the means can't spend the time to study and move into these fields. And I'm really interested in sort of making sure that everyone has access to these career paths.
Well, how can people find out more about you, and how can people find out more about the Institute?
So the Institute is at sci.edu. Learn all sorts of cool things about us from that. But I would say to look at webbtelescope.org and hubbletelescope.org or hubble.org,
Okay.
hubblesite.org, sorry, for information about what those observatories are doing and discovering every week. I even have a press release up there pretty recently. If you look for my discovery in the Serpens cloud complex with Webb, you'll see my name pop up. So that's fun.
Nice.
The other thing I guess I would mention is I did write. I do like to write. I do like to talk to people about science. And although I'm far from an expert on black holes, that has been a really interesting topic recently. And I thought it was one that kids might want to learn more about. So I actually teamed up with a children's author and wrote a book called Black Holes by Norwood House Press. And it is for people from ages 9 and up to adults. And it's just a neat story of the recent discovery of the first picture ever taken of a black hole, and kind of the story that led up to that. So,
wow.
As for me, I think, just you can look up my work. I think I have a website, but it's very old and primitive.
All right. Well, and it's August, so folks listening, it's the height of summer. Look up at the night sky, and wherever you are in the world, we're all looking up at the same sky. So I think it unites us in a way, and I mean, it's a fascinating subject that will keep us interested forever, basically. So
I'm thankful for that.
yeah. Yep. Well, Joel, it's been a pleasure, and thanks for coming on the show.
No, thank you very much for having me.